I am Patil PB, junior college teacher at sgm College Karad, which is a branch of Rayat Shikshan Sanstha. Now today we are going to see the article hysteresis. When unmagnetized ferromagnetic material is in the form of rod and is placed inside a solenoid, then we know that it gets magnetized. If we know the susceptibility chi of the material, then we can determine the magnetizing field as by knowing the value of chi, we can determine the value of magnetization. H is, and we also know that H is equal to N. N is number of turns of the solenoid coil and I is current in the coil. H is equal to N. Knowing chi and H, magnetization can be determined. And also we know that H is equal to B upon mu 0 minus M. We can modify this equation as or H plus M. B is equal to mu 0 H plus M. Now knowing the values of H and M, we can easily determine the value of magnetic field B. Now if we plot a graph of magnetizing field against current or magnetizing force, we get hysteresis curve for ferromagnetic substance. I have drawn this curve on the blackboard. O is a point. We can say that the substance is in unmagnetized state. If this unmagnetized ferromagnetic substance is kept at the core of the solenoid and current is passed through the solenoid. If we increase the magnetic intensity H, flux density also increases. Flux density also increases. Reaches at point A. But remember, this increase is non-linear. It is not linear increase. Therefore, we get curve like this. At point A, if we increase again the value of current, then magnetic flux does not increase. It means at point A, we achieve saturation. All domain axes are turned in the direction of the field. Now, if we reduce the current in the solenoid coil, path is not retraced, but B decreases. I decreases, B decreases, and we reach at point B. At point B, remember that H is equal to 0, but B is not equal to 0. At point B, H is equal to 0, but B is not equal to 0. This point, the value of B the value of B is called retentivity or remanence of the ferromagnetic material. Current in the solenoid coil even becomes zero. Magnetic field does not become zero at point B. This point B is called retentivity. Now, if we pass current in opposite direction, then magnetic flux decreases and we reach at point C. Here at point C, B is equal to 0, but H is not equal to 0. At point C, B is equal to 0, but H is not equal to 0. This point C is called cursivity. This point C is called cursivity of the ferromagnetic substance. We can say the domain axes are randomly oriented in ferromagnetic substance. Again at point C, if we decrease the current, we reach at point D. Again we occur saturation in opposite direction. If we reduce the current, we reach along the curve DE. We reach along the curve DE. At point E, again H is equal to 0, B is not equal to 0. Here at point E, domain structure is present, but magnetization is reversed. Axis of domain are in opposite direction in ferromagnetic substances, but domain structure remains present. And if we increase again the value of current, then we get the curve EFA. By increasing value of current, magnetic flux also increases and we get curve EFA and we reach again at point A. Now this whole O, A, B, C, D, E, F, A, this loop is called hysteresis loop. Hysteresis loop of a ferromagnetic substance. Remember, at point A, saturation occurs. At point B, S is equal to 0, B is not equal to 0. This point is called retentivity of the ferromagnetic substance. At point C, B is equal to 0, but H is not equal to 0. This point is called cursivity. Domain axes are randomly oriented. Here, all domain axes, at point A, all domain axes are in the direction of the field. Here, domain axes are randomly oriented. And at point E, again, H is equal to 0, but B is not equal to 0. Here, domain axes are in opposite direction, but domain structure remains present, but axis of domain are in opposite direction. A, B, C, D, E, F, A. This loop is called hysteresis loop of a ferromagnetic substance. Now, very small articles in this chapter remains permanent magnet and electromagnet. Permanent magnet and electromagnet. First we will see what is electromagnet. When soft iron having large permeability and small amount of retaining magnetization power is placed at the core of the solenoid, and if we pass the current through the solenoid, we know that this soft iron gets magnetized, and magnetic flux of this solenoid increases by 1000 volts. Magnetic field of the solenoid increases by 1000 volts, and this solenoid becomes electromagnet. Remember, to make electromagnet, we have to use a material which is soft ferromagnetic material, soft iron ferromagnetic material, which is kept at the core of the solenoid coil. And when current is passed to the solenoid, the magnetic flux of the solenoid increases by 1000 volts, and this solenoid becomes an electromagnet. By using, what are the uses of electromagnet? In day-to-day life, we see electric bell, loudspeaker, circuit breaker circuit, and in research laboratories we use electromagnet. Remember, here we use a material which is soft iron to make electromagnet, and to make permanent magnet we are using a material which is hard iron. To make permanent magnet we have to use hard iron. Same procedure, the hard iron is kept at the center of the core of the solenoid, and when current is passed through the solenoid, this hard iron gets magnetized. When current is passed for a longer time, then this material acquires magnetism, and even if we switch off the current through the solenoid coil, we found that this hard iron does not lose its magnetism. This iron becomes a permanent magnet. To make permanent magnet, soft iron is not used. Soft iron is only used in electromagnet. Soft iron loses magnetism when current is switched off in the solenoid, but hard iron does not lose its magnetism even current is switched off in the solenoid coil. Now, last article of this topic is magnetic shielding. I will draw simple diagram. This is a magnet. Another magnet is kept in front of first magnet. We know that when two magnets are kept near, the uniform magnetic field is produced at the gap between these two magnets. Uniform magnetic field. So we draw parallel lines This indicates that, parallel line indicates that in the gap between the poles, uniform magnetic field is produced. Now, if we put a soft ferromagnetic material is in this magnetic field, if we put a soft ferromagnetic material in this magnetic field, then it is found that all these magnetic lines of force will pass through this soft ferromagnetic material, and very few lines will pass away from the soft ferromagnetic material. All lines will pass. Means when I will put suppose that if I put this material, this is a ring of soft ferromagnetic material, and I found that you will find that all magnetic lines maximum number of lines of force will pass through this soft ferromagnetic material. This is called magnetic shielding. When these lines pass through all soft magnetic material, there is crowd of lines inside the ferromagnetic material. This is called as magnetic shielding. Now the theory of this chapter is now over, and we have to see some few examples in this topic. The first example is when a plate of magnetic material of size 10 cm by 0.5 cm by 0.2 cm is located in magnetizing field of 0.5 into 10⁴ ampere per meter, then a magnetic moment of 5 am² is induced in it. Find the magnetic induction of the rod. Now what is given in this example, we will write first. Data. Size of the plate is given, length, breadth and thickness. Then we will first determine its volume. Volume is equal to 10 into 0.5 into 0.2. 10 multiplied by 0.5 means 5. 5 into 0.2 means 1 centimeter cube. And we will convert this in SI unit, meter cube. 1 into 10⁻⁻⁶ meter cube. This is volume of the plate. Magnetizing field, H is given. H is 0.5 into 10⁴ ampere per meter. Magnetic moment of 5 am². Magnetic moment, new notation is small m, 5 am². This is given, and we have to find the magnetic induction. We have to find the magnetic induction. Now, I will write here the formula to determine magnetic induction. What is that formula? We know that B is equal to V0 in bracket H plus M. B is equal to V0 into bracket H plus M. And this is capital M, this is magnetization. We have given small. Now, Hysterisis permeability of free space constant, we know that. H is given. Magnetization means magnetic moment per volume. We can write usually this equation as mu0 H plus small m upon V. Capital M is small m upon V means capital M. Substituting these values now, mu0 is 4 pi into 10 raised to minus 7 H 0.5 into 10 raised to 4 plus m is given 5 divided by V. We have determined it as 10 raised to minus 6. Four pi into 10 raised to minus 7. We can shift this point here. Then this becomes 5 into 10 raised to 3. 10 raised to minus 6. 5 into 10 raised to 6. We will take this 10 raised to minus 7 inside this bracket. 4 pi. 10 raised to minus 7, 10 raised to plus 3 means 10 raised to minus 4 plus 10 raised to minus 7 into 10 raised to 6, 10 raised to minus 1. 4 pi. 4 into 3.42. 5 into 10 raised to minus 4 means point not 5. And 5 into 10 raised to minus 5 is 0.5. Add these two. And 4 into 3.14 is 12.56. And after adding this, we will get 0.500 first. This multiplication is solved by using logarithmic table, and we get answer as 6.286. And unit of magnetic induction is passive. This is final answer of this example. Thank you very much.